Welcome back, everybody, to episode 49 of the Quantum Science Seminar, which today will be all about quantum information. If you have any questions, we would like to hear them. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of your screen. You should also note, as always, we have a 30-second time delay between what we do here and what you see as live on YouTube. And with this, I'd hand over to Thomas, who will introduce our speaker today.
So then, good afternoon, good morning, everyone, and welcome to the Quantum Science Seminar with Scott Aronson. So I think Scott is a prime example why quantum computing doesn't have to be so much about quantum physics, but we should actually focus a lot on the computational aspects, and therefore it's a great pleasure for me to introduce you here. So Scott has a strong focus on computing. He did his bachelor's at Cornell, he did his PhD in Berkeley, to later on do postdoc positions both at IQC in Waterloo as well as in Princeton, and subsequently had an assistant professor position at the MIT, and now he's a full professor in Austin, Texas. I guess most of you are familiar with Scott's work, and I'm very much looking forward to his presentation. So thank you very much for coming.
All right, well, thank you so much for inviting me to this. So I want to briefly introduce you to a topic that's been in the news a lot, the past couple of years. In fact, it entered the news just a few months before COVID took over the world. And this is quantum computational supremacy, the use of a quantum computer to do some benchmark task faster than we know how to simulate it with any existing classical computer. And this is a topic that I got into about a decade ago when some of us realized that there was a real prospect of achieving this. And at the time we came to it just by thinking about computer science, about complexity theory. But thinking about how would you actually demonstrate quantum supremacy, brought us into contact with experimentalists, in a way that was very new for me, and it's been, an incredibly fruitful interchange, where we will suggest things, they will tell us that it can't be done, but here's some other thing that can be done, and is that interesting from a computer science point of view? And it has culminated over the last couple of years with two claims to have actually achieved quantum supremacy for some artificial sampling benchmark, one by Google, the other one by USTC in China. So I have been to see the lab in Google, so I can testify that this picture here, which is what came up when I did a Google image search for quantum computer, this is not exactly what it looks like when you tour the lab. Although when I do tour the lab, I have to take their word for it, that this is the dilution refrigerator, and is not the fridge for leftovers or something. Well, okay, they did. Okay, I guess even I can tell those apart. But all right. So what is quantum supremacy? The term was coined in 2012 by John Preskill, and but the basic goal or idea goes back all the way to the beginnings of quantum computing as a field in the early 1980s, and it's just a term that denotes the first use of a quantum computer to do something that is hard to simulate with a classical computer, or that we have good reason to believe, let's say, is outperforming what you could do with any existing classical computer. You may notice I did not say anything about the task being useful. Okay, that is not part of this. So you should think of the Wright brothers airplane, or which was not in itself a useful airplane, for passenger travel. It could only, hold one person, right? But its point was to demonstrate that, a heavier than air flight actually can be done, using technology that now exists on Earth, right? Or think of Enrico Fermi's nuclear chain reaction in the 40s. So, we would like to sort of prove the point that a quantum computer, can do something faster, right? And it's not just a matter of you can make 2 or 3 qubits, in an entangled state, but you can actually do something that is beating what you could have done with a classical computer. Okay, and so what we will demand as part of this benchmark is that the task be well defined. So it's not enough to just point to some complicated system that you've built in your lab and say, well, you can't simulate all of the chaotic, details of what this does with your classical computer, or if you can't, then this device achieves supremacy for the task of simulating itself, right? We are not going to count that. Okay, you have to be able to give a self-contained mathematical description of what problem your device is supposed to solve, such that it would be meaningful to say that your device had failed to solve that problem, okay? And such that a classical computer, can also solve that problem, at least, given enough time, okay? And so now we can compare the classical computer against the quantum computer, on solving the same well-defined benchmark problem. And, we want to see that the quantum computer is faster, not just a little bit faster, but, ideally many orders of magnitude, and not for incidental reasons, but, I want the explanation, the only available explanation for why it's faster to be about, the enormous dimensionality of quantum states, right? The exponentiality of Hilbert space. So that is what we are after here. Okay, so since the landmark discovery of Peter Shor in 1994, that quantum computers could efficiently factor numbers, we have known sort of what is the gold standard for a quantum supremacy demonstration, right? If you could build a quantum computer that could find the prime factors of random 10,000 digit numbers, then there would not be a whole lot of arguing about it, at that point. Okay, even the computer scientists or the physicists, who still today, firmly believe that quantum computing is impossible, that it will never scale or never really work. I mean, they would have to admit at that point that something interesting was going on, because they could easily check the prime factors for themselves, right? They could easily multiply them, right? And so there's no trust, in the device that is needed at that point. Yeah. So I like to say that for me, Shor's algorithm really is what put quantum computing, on the map for the wider world, because it meant that quantum computers would be useful for breaking most of the encryption that currently protects the internet. Not clear that that's good for humanity, but at least it's useful for whatever intelligence agency gets it, if no one else knows that they have it. So now quantum computers would probably be useful for a few other things. The original application that Feynman and Deutsch talked about in the 80s was, they'd be useful for simulating quantum mechanics itself. That might still be, the most important commercial application that we know of today. And then, there is enormous interest and hype in potential applications of quantum computing to optimization, to machine learning, to big data, and things like that. I have to say that those applications are a lot less clear. I mean, I think that it will take longer until we can see a real advantage with a quantum computer for those problems, and the advantage that we think that we could get would be more modest. Okay, those are the applications of quantum computing that tend to be talked about. But the perspective that I would like to take is that the number one application of a quantum computer for me personally is just disproving all of the people who said that it could never work, right? You could say, similar to, what is the application of the Large Hadron Collider or of the, LIGO for gravitational waves, right? It is to, show that this phenomenon is real, okay? Take some phenomenon that physicists have just written down on paper, in this case, the exponentiality of Hilbert space and our ability to harness it to do an actual computation and show that is real. Okay, so so people for a quarter century now, have been working to try to build scalable quantum computers, that would be able, for example, to run Shor's algorithm, and factor, n-digit numbers in only about n² steps. Unfortunately, this turns out to be a staggeringly difficult engineering problem. And the central reason for that is that quantum states are very fragile, right? They will, lose their quantum coherence, typically in a very short time scale, because they are constantly being measured by the environment. They're constantly interacting with the environment, and if you take a qubit, and and the information about whether that qubit was a 0 or a 1 leaks out into the environment, then it is as if the environment has measured that qubit. The effect on the qubit is to collapse its state. So what this means is if you want to build a useful quantum computer, you have to keep the qubits incredibly well isolated from their environment, but at the same time, not perfectly isolated, because the qubits have to be interacting with each other, and you have to tell them exactly how they should do so. Okay, so these are such hard problems that there were serious physicists and computer scientists who said this will just never be done. You will never manage to get a speed up this way. Now, what changed most people's minds, in the mid 90s, was the discovery of quantum error correction and quantum fault tolerance, which said that there are these very, very clever schemes by which you can do quantum computation even with noisy qubits, okay, by encoding the information that you care about across the collective states of hundreds or thousands of qubits, okay, so that even as the information leaks into the environment, you can dynamically detect that and correct for it. Okay, the problem with these methods of fault tolerance is that they themselves have a huge engineering cost. So it might be that to build a quantum computer that could run Shor's algorithm to factor a number with, say, a few thousand bits, in theory that would take only a few thousand qubits. But if you need this error correction and fault tolerance, then each qubit has to be encoded using thousands of physical qubits, using any of the known schemes. And so then you're talking about millions of physical qubits, okay? And that is just out of reach at present. Within the last couple of years, we have finally seen programmable quantum computers with 50 or 60 or 70 qubits, as I'm going to talk about. Okay, so that is the state of the art. Achieving quantum supremacy via Shor's algorithm, that is just going to take a lot longer. Okay, and so a decade ago, some of us started thinking about the question of, well, is there an easier route to demonstrating quantum supremacy? Is there a more direct route that would not require you to build a full fault-tolerant quantum computer with millions of qubits? And what several of us noticed around the same time is that there is something else that you can do. Namely, you can switch your attention from problems like factoring, which have a single right answer, that you either find or you don't, to what are called sampling problems. Okay, a sampling problem is one where we describe some probability distribution. So some distribution over, let's say, strings of 50 bits, of which there's 2 to the 50th power, right? And now the goal of the computer is to output a sample from that distribution, okay? And we can then run the computer, we can see the samples that come out, and we can do statistics to try to test whether the right distribution is being sampled or not. Knowing what we're looking for, knowing what the distribution is supposed to be. Okay, but we're now talking about problems where there's an enormous number of possible right answers, so to speak. Right. The question will just be: are you sampling the different right answers with something like the correct probabilities? Okay, and so a decade ago, my then student Alex Arkhipov and I started thinking about this in the context of what we called boson sampling, which was a proposal for an extremely rudimentary quantum computer, where all you would do, in this case, was just to generate a bunch of photons and then pass them through a network of beam splitters, simple optical elements. And then you would just measure where in each output mode, in each final location, how many photons were there. Okay, and that you would get some sample from the probability distribution over all of the possible places where all of your photons could land. Okay, so and that's it. Okay, there's no interaction among the photons. This is not, we don't think, a universal quantum computer, or even for that matter, a universal classical computer. Okay, but what we argued was that nevertheless, the distribution over photon states that this kind of simple optical device would sample is not something that we expect a classical computer to be able to sample easily. In particular, if you have n photons, then the best classical algorithms that we know for sampling the same distribution would take time that grows like 2 to the n power. Okay, so with 5 or 10 photons, you can do it, but with 50 photons, you'd already be reaching the limit of what the biggest supercomputers on Earth could do, and with 100 photons, you would be well beyond that limit. Now, we were not able to prove that. I mean, in computer science, it is famously difficult to prove that problems are hard. If you've heard of the P versus NP problem, that is what that's all about. But what we're really good at in computer science is passing the blame to someone else, right? So, the entire theory of NP completeness is about, well, I can't prove that my problem is hard, but I can prove that if you could solve it, then you could solve 10,000 other problems that, people have been trying to solve for half a century. So, it's not my fault that I wasn't able to solve it, right? And so, the main technical thing that Arkhipov and I did with boson sampling is that we gave such a reduction argument for the hardness of boson sampling. Okay, we said that if you had a fast classical algorithm that could efficiently simulate a boson sampling device, then that would really have dramatic consequences for classical theoretical computer science. It would lead to something called the collapse of the polynomial hierarchy. If you don't know what that means, you could take my word for it that it's bad. It would be almost as dramatic as P equaling NP, although maybe not quite. That was if you've had a classical computer that could sample from exactly the right probability distribution. Now, in practice, not even the physical device will be able to sample exactly the right distribution, and so we ought to allow noise. We ought to allow sampling from some distribution that is merely close to the prescribed one. And then it becomes a much more complicated question, to say, is that also hard for a classical computer? And then, we had to make some stronger assumptions. Okay, but we were again able to give a hardness reduction, saying if you believe this sort of plausible conjecture in classical theoretical computer science, something that has nothing to do with quantum computing, then even simulating a noisy boson sampling experiment should be hard for a classical computer. Okay, so now around the same time as us, others, especially Bremner, Jozsa, and Shepard, were having similar ideas, and we're also proposing to do quantum supremacy based on sampling problems. And so this idea really coalesced around that time. And then what happened was people started doing actual experiments with boson sampling around 2013, 2014. Initially, it was with just 3, 4, 5 photons. So, your classical computer is not going to break a sweat to simulate that. It was clearly, going to be a challenging engineering problem to scale it up to get, 50 photons all traveling through your network at once and all detected at the same time, right? This is, a lot of balls to be juggling at once, so to speak. But people were working on that, and then in the meantime, in around 2015. Google hired John Martinez to head up its lab in Santa Barbara and build superconducting qubits, build chips, that would integrate, a bunch of what are called Josephson junction qubits, in a programmable way. And they decided around that time that they were going to make the demonstration of quantum supremacy, their central goal, for the next 5 years or so. And they decided basically that, they wanted to do something like boson sampling, but that was more adapted to their hardware. Okay, so I and others in the theory community were involved in conversations with Google, around 2015 about, what exactly, once they are able to build this chip, what exactly should they do with it, right? If you have 50 qubits, what do you do with them that we're as confident as possible will take 2 to the 50th time to simulate with a classical computer? Okay, so that was kind of how all of this was born, and this brings us to their announcement. Well, I guess in late 2019, when they finally first the paper actually leaked to the press by accident. Then it was a month later was a cover article in Nature, and so Google built a chip with 53 superconducting qubits on it, what they called Sycamore. If you're wondering why 53, it sounds like a weird number. Well, they built 54 in a roughly rectangular array, and one of them didn't work. Okay, which is apparently common when you fabricate these chips. They then take the chip and they place it into a dilution refrigerator. That's this upside down wedding cake thing over here, and they cool it to about 10 millikelvin. Okay, so 1/100th of a degree above absolute zero. That is what causes the currents going around these in the chip to superconduct. Okay, which is a quantum phenomenon, which is what allows your qubits to be qubits, to exist in superpositions of 2 different energy states that you can label by 0 and 1. Then you have a classical computer, outside of the dilution fridge, which you can use to, control a microcontroller, which is sending signals into the fridge into the chip, telling each qubit exactly what it should do, okay? Exactly which of its neighbors, you know, on the chip it should be interacting with, and when and how. Okay, so what they did is, you know, they used this chip to sample from some probability distribution over strings of 53 bits, right? So each time you apply a sequence of operations to the qubits, that's your quantum circuit, that's like your program, basically, and then, you know, that produces some horrendously complicated entangled state on all 53 of the qubits. And then you measure that state. You measure each qubit to see if it's 0 or 1. And that gives you a sample each time from some probability distribution over 53-bit strings. You know, the same distribution each time. So now, you know, this distribution, there are 9 quadrillion different strings being sampled. Okay, but crucially, not all of them are equally likely. Okay, there are biases that are supposed to make some of the strings a little bit likelier than others, and those biases are really the key to the whole thing. Okay, the biases are going to be the signature of quantum supremacy that the experiment is looking for. Right, that the use of quantum interference to boost the probabilities of some outputs relative to others. Okay, so, you know, but just to give you some numbers, so you know, the circuit that is applied to these 53 qubits has about 1,000 operations. You know, 1,000 1 and 2 qubit gates. Okay, the gates are arranged into about 20 layers, 20, you know, or, you know, within each layer, all the gates are done in parallel. You know, now, you know, there is a lot of noise in the system. So, you know, when each time you take a sample, what you're seeing is basically 99.8% uniform randomness. Okay, just, you know, the uniform distribution. You're seeing 0.2% the distribution that you wanted. You know, the bias distribution, where, you know, where some strings are likelier than others. So you're trying to extract that 0.2% signal out of the noise. Now, the good news is that the chip is very fast. It is able to take each sample in about 40 microseconds, which means that in just a few minutes, you can take millions of samples. Okay? And that actually is enough to extract a signal, you know, even in the presence of that much noise. And that is exactly what Google did. Okay, so you know, now what is the actual sequence of operations that we tell the qubits to perform? Well, here, you know, I feel a little bit sheepish because the proposal is so trivial in a way. All we do is we give it a completely random sequence of operations. Okay, so we just tell, you know, the qubits to just sort of scramble up their state, you know, as rapidly as possible, as it were, but you know, do so in a very specific, you know, and precisely reproducible way. So we send a random sequence of gates where each gate is you know, between qubits and their nearest neighbors. So like in the animation on the left, right, we can stagger the gates so that every qubit can propagate a signal to every other qubit. And so, you know, so formally what we're doing is we're sending this circuit C to the quantum computer. We're asking it to send back a collection of samples, call them S1 up to S sub k, from D sub C, which we'll define as the probability distribution over n bit strings that you get by taking the circuit C, applying it to some standard initial state, let's say the all zero state, and then just measuring each qubit in the 0 or 1 basis. Okay, now the really key question with this whole scheme is, well, supposing that you do this, supposing you get the samples, how do you check them? How do you know if the quantum computer worked or not? Okay, what do you do, right? Well, of course, if we could run this experiment for long enough, then we could just reconstruct the entire probability distribution, and then we could check it against a calculation that we did with our classical computer, using, maybe a gigantic supercomputer if we need it, right? And we could see whether the probabilities would match, right? Unfortunately, we don't have nearly enough time to do that, okay? Because, again, there are like 9 quadrillion possible outputs, right? And we maybe have time to see a few million outputs. Okay, so what we have to do instead is some statistical test on the outputs that we see that will tell us, are these outputs, preferentially the ones that were predicted to be more likely, if you knew the distribution. Okay, so the good part is that we know the circuit C. Okay, so with our classical computer, we can take the samples that we see, we can calculate the ideal or the predicted probabilities for each of those samples, S1 up to Sk, and we can then check whether those probabilities are anomalously large. Okay, and again, that is exactly the kind of test that Google ended up doing. Okay, so they applied a test that they called the linear cross-entropy benchmark, or linear XEB. Okay, and this test is, one of the simplest things you could possibly write down. All you do is, with brute force on your classical computer, which you can still do if it's merely 50 or so qubits, it just takes 2 to the 50th time. You calculate the probabilities for each of those samples to be generated by an ideal quantum circuit, and you add them all up, and then you will judge the quantum computer to have succeeded if and only if this sum exceeds a certain threshold. Okay. Now, what we expect is that if you were just picking the strings at random, since there's 2 to the n of them, their average probability would be 1 over 2 to the n, right? And so if I add up k of these probabilities, I'm going to get about k over 2 to the n. Okay, but again, when we do this experiment, some outputs are likelier than others, right? We'd expect to never see a sample that has probability 0, and if some sample has a probability of 1 in 5 quadrillion, we should be twice as likely to see that one as one that had a probability of 1 in 10 quadrillion. Okay, so there are biases. Now, ultimately, the origin of those biases is quantum mechanical interference. Okay, so each amplitude in our final quantum state is a sum of exponentially many contributions, right? Those contributions all being complex numbers, which could point every which way in the complex plane. Okay, and typically what happens is that most of those contributions just cancel each other out. Okay, but they leave a tiny residue left, left over. Okay, and that residue, or rather its squared absolute value, is the probability that you will see that output. Okay, so and just by chance, some of those residues will be larger, than other ones. In fact, the probabilities will be you can show will look like exponentially distributed random variables. Okay, so some will be twice as likely, 3 times as likely, and so forth. And if you do the calculation, what you find is that with an ideal quantum computer, the value of this, the expected value of this sum should be exactly twice what it would have been, if I just picked the samples completely at random, right? So, So, purely random sampling should give me k over 2 to the n. So if I look at this constant b here, that would be equal to 1. Whereas an ideal quantum computer should give me 2k over 2 to the n. Okay, so the constant b should be 2. Okay, and so now we have a situation that is extremely similar to the experiments that violate the Bell inequality, for example, if you know about those, right? You have an inequality that we think is satisfied by any efficient classical computer, namely that this sum is going to be at most about k over 2 to the n. And then, we know that a perfect quantum computer would violate that inequality, okay? Would do better than that. And what we're looking to see is, do we do not necessarily the ideal thing, but do we get any value that is above the classical value, right? And so, Google in its experiment reported a value of this constant b that was about 1.002. Okay, so very far from the classical, very far from the ideal value of 2, but above the trivial value of 1. Okay, and they were able to show to like 10 or 20 sigmas, that yes, this 1.002 really is larger than 1. It's not just a statistical fluke. Okay. So that was the basis for their claim of quantum supremacy. Now, some of you might know that other people, when you put out a claim of quantum supremacy, you're basically just like it's not something like landing on the moon where you just you do it and it's clear to everyone, right? This benchmark is all about beating classical computers, and classical computers can fight back. Okay, so quantum supremacy is a milestone that can be achieved and then unachieved later, right? If someone figures out how to simulate what you did quickly with a classical computer. Okay, so you have to allow for a back and forth to try to settle that question. Now, in its original paper, Google estimated that the best algorithm that they knew, running on their supercomputer, that had 1 million cores on it, would have taken about 10,000 years to simulate what the quantum computer had done in 3 minutes. Okay, and that number then got widely repeated in the press, but that was over optimistic. Okay, and a few weeks later, IBM, which is Google's main competitor in superconducting qubits, put out a preprint saying, well, we reject Google's claim of quantum supremacy. And here was their argument. They said, if you used Summit, which is literally the largest supercomputer on the planet right now, which IBM installed a few years ago at Oak Ridge National Lab, it fills 2 basketball courts, and it's got 250 petabytes of hard disk space. Okay, they said, well, that is enough hard disk space that you could just literally take the entire quantum state, the whole vector of 9 quadrillion amplitudes, and you could just write it to hard disk. Okay, and once you had done that, you could simulate Google's experiment in only about 2.5 days. Okay, now IBM didn't actually do this. It would be absurdly expensive to get to commandeer this world's largest supercomputer for that purpose. Okay, but I believe them that this could be done. Now I think that it's embarrassing for Google that they sort of they weren't thinking about this. They were thinking about that you would have to store the intermediate results in RAM, and nobody had 250 petabytes of RAM. But at the same time, I feel like if this is the you could say if this is the best classical simulation that anyone can find, then it is almost like a backhanded compliment, right? It is like saying if this is what it takes to classically reproduce the Google experiment, then it is clear that the quantum supremacy experiments, are on track to decisively win. In just I mean, already we've gone from 53 qubits to apparently about 72 qubits in the latest experiments, right? And each time you add another qubit, you double the amount of hard disk space that this type of approach would need, right? And you double the number of parallel processors that would be needed, okay? And no one is going to, fill the entire planet with these summits. So, it's almost like the Google versus, it's almost like the IBM versus Deep Blue chess match in the 90s, right? Except with the historic irony that IBM is now in the role of Kasparov, right? They're saying like, yeah, with heroic effort, we can maybe, match the supremacy experiment now, but if it's a fight right now, then in a couple of years, it stops being a fight, right? Now, people have continued to work on this over the last couple of years, and people have since said, well, we could simulate. There was a very recent paper that said, we could simulate Google's supremacy experiment using what are called tensor network methods. Where you wouldn't need, the world's largest supercomputer, and it would again take only a few days with much more modest resources. But, often, these tensor network methods, you could evade them by just changing the verification test. Okay, so for example, if you also check that the strings S sub I are all very different from each other, that they don't share like most of their bits in common, then then that would be enough to evade the most recent tensor network results. Okay, so the point is this is it's a race, right? We expect that quantum computing will eventually win the race, but but right now it's kind of you can follow it like a sports match, where people can improve the classical simulation, then they can also improve the quantum supremacy experiment. Now, I think that what would really change the situation would be if someone discovered a way to classically simulate these quantum supremacy experiments that beat the 2 to the n barrier. Okay, so right now all of the simulations methods that we know about are taking time that scales at least like 2 to the power of the number of qubits, right? And and you can sort of try to be clever about it in all sorts of ways, but at the end of the day, there is this exponentiality there, right? And I think that a key theoretical question is, well, is there some clever shortcut, by which a classical computer could spoof the samples, without having to simulate the whole quantum circuit, needing 2 to the n time. So with two of my two students, Li-Ji Chen and Sam Gunn, we gave some theoretical evidence against that possibility. Again, a reduction argument, passing the blame kind of argument. But what we were able to show was that if you had a fast classical algorithm that could do anything whatsoever to spoof Google's linear cross entropy benchmark, so, not only sample from the same distribution, but just do anything whatsoever that would pass their test, right? Pass their benchmark test, then that would imply that there would also exist a fast classical algorithm to estimate amplitudes in random quantum circuits, faster than we think that could be done. Okay, so it's not decisive, but there's some evidence that you're not going to spoof the test that Google was doing without some major breakthrough on the general problem of how do you classically simulate a random quantum circuit. Okay, now just in late 2020, 5 or 6 months ago, the group of Chaoyang Liu and Jianwei Pan at USTC in Hefei, China, announced a second demonstration of quantum supremacy. And this was using the original boson sampling proposal of me and Alex Arkhipov. Okay, so they literally built, a gargantuan optical table. That's what you see in the picture there. And they sent, on average, about 50 photons through it. It's a variable number of photons because they're in what are called Gaussian states, but it's 50 to 70 on average. And then, they detect them. There's about 100 optical nodes in this experiment. And, this is the first claimed demonstration of quantum supremacy based on photonic quantum computing, rather than superconducting. They do have one big advantage over Google's experiment, which is Google's experiment had about 10 to the 16 or 10 quadrillion possible output states. The newer experiment has 10 to the 30th possible output states, which means that simulate, that attack that IBM proposed, where you just store all the amplitudes on a supercomputer, in a gigantic hard disk, that's not going to work here because no one has a hard disk, with that can store 10 to the 30th amplitudes in it. Okay, but the trouble is there is a fair amount of noise in the experiment, and it's something like 70% of the photons get lost on the way through. Only 30% of them are detected, and the jury is still out on the question of will those imperfections in the experiment enable a much faster classical simulation. So far, no one has figured out how to do that, but some people think that it's possible. And so, so people are still working on that. Now until very recently, it was said that, these quantum, supremacy experiments based on sampling, maybe they're interesting, but they have no application in and of themselves because, all they're doing is they're generating a bunch of random bits, right? Who cares about that? A few years ago, I realized that might actually be useful for something. Okay, it's true that if you just want random bits, you can just take a Geiger counter, put it next to some radioactive material or something, right? Or just look at the last digits of the Dow Jones average, right? There are lots of ways to get random numbers, but there are some applications where what you want is a gigantic randomness beacon. So let's say on the internet, you want some source that is publishing a huge beacon of random bits, and where everybody has to trust that these bits are really random, right? The NSA can't predict them, Google can't predict them, right? No one secretly knows a pattern in them. An example of such an application, what are called proof of stake cryptocurrencies, like the next generation Ethereum, where they constantly run a lottery to decide who gets to add the next block to the blockchain, and so everyone has to trust that this lottery was really done randomly, right? And so what I noticed a few years ago is that these sampling-based quantum supremacy experiments, the ones that we already have, they could be repurposed to get a sort of certifiable randomness beacon, right? And the way that this would work is that you use your quantum computer to solve the sampling problem of sampling from the output distributions of circuits that are provided by skeptics, and once in a while the skeptics will have to verify the results, meaning verify that the outputs pass that linear cross entropy benchmark. Okay, and then if they pass that benchmark, then we don't expect that even a quantum computer would be able to generate samples that pass that benchmark in a secretly deterministic way, right? The only way it could do it would be by generating, bits with a lot of real entropy in them. And that entropy could then be extracted and used for cryptographic applications. I don't know if this will be useful or not, but Google has been working to demonstrate it. And if it were useful, then it could be the first application of quantum computing in a sense, because it is a thing that you could already realize even using the noisy 50 qubit quantum computers that already exist. Okay, so there are a lot of exciting places to go next. I think maybe the biggest theoretical problem in this whole area is, can we do these sampling-based quantum supremacy experiments, but in a way where a classical computer can easily check the results, where we don't have to do this brute force 2 to the n classical computation in order to verify the results, right? Because right now we're inherently limited to 50 or 60 qubits. Like if you did this experiment with 100 qubits, well, it might work, but we could never prove it, right? Because there's no classical computer that can spend 2 to the 100th time to verify the result. Okay, so we're inherently limited in that way, and the way to break that would be make make the results efficiently verifiable with a classical computer. Right, factoring does have that property, but factoring, as far as we know, requires a full fault-tolerant quantum computer, and that's still far in the future. So can we do any verifiable quantum supremacy in the near-term era? I think that's a huge challenge. And then, replicate quantum supremacy in other hardware platforms like trapped ions. Figure out, whether these claims of quantum supremacy really stand. Can we design better classical simulation algorithms that would break them? Or in the other direction, could we get better theoretical evidence for hardness? And then, could we improve my randomness scheme to make it more practical? So to conclude, Google and USDC may have achieved quantum supremacy for sampling tasks, building on a lot of, what seemed at the time like pretty useless complexity theory. Okay, now even if true, this leaves the enormous challenges of building a scalable, fault-tolerant quantum computer, right? The Google and the USDC experiments had no error correction whatsoever, right? And a demonstration of useful error correction is, I would say, is now has become the central experimental holy grail in quantum computing. Now that we have or seem to have quantum supremacy. Okay, but quantum supremacy by itself, I think, is already enough to refute the people who said that quantum computational speedups are impossible in our world. So I think that that's a big deal. Okay, now, it was thought obvious for years that sampling-based supremacy experiments had no applications. Things like my certified randomness protocol might change that, although, challenges remain in making it practical. Okay, so that's so thanks for listening. I apologize. I just have like 7 or 8 minutes for questions, and then I have to go to another meeting, but I'm happy to take questions.
Well, thank you very much, Scott, for the really nice talk. We did have lots of questions, so we'll try to get through as many as we can in the time we have.
All right, let's see if we can do a speed round.
So, so as you said, in computer science, it's difficult to prove that things are hard. From a computer science perspective, to what extent is quantum supremacy then something absolute? And to what extent is it really a shifting bar that depends on how good the classical hardware and calculations are?
Well, I mean, I would say it is a shifting bar, right? But, there is better evidence and worse evidence, right? So, and what is crucial to understand here is that, the advantage that you're hoping to get with a quantum computer is an exponential advantage, right? So, it's not like a factor of 1,000 or or some fixed factor that Moore's law is just going to wipe out in a few years anyway, right? You are really hoping to do something in, n steps quantumly that would take 2 to the n steps to simulate classically, okay? And, so there is a question of, well, what is n? First of all, how large is n, right? And is 2 to the n really, large enough? Is it out of reach? And then there's also a question of, do you really need 2 to the n, right? Is there a classical shortcut, that will do better than that? Okay, but so I think the goal is to get more and more solid evidence on those questions. Do it with a large enough number of qubits and do it an experiment where we know based on a widely believed theoretical assumption that you will need 2 to the n time to simulate, and then I think that the burden of evidence decisively shifts at that point to anyone who thinks that quantum supremacy was not achieved, right? It then becomes their problem to refute the claim by giving a faster classical simulation.
So so we got several questions on sort of how many resources then are sort of too many resources. Should we consider all possible classical resources in the entire universe? And what you're sort of saying is, in the end, the question is one of scaling and practicality, rather than allowing the classical resource to be anything.
Yeah, I mean, what I would say about that is that we are. Ultimately, with what we hope that quantum computers will someday do is, solve problems in a few minutes, at least some very, very specific ones like factoring. But that with even if you converted the entire observable universe into classical computers, then it would take them trillions of years, right? They could not do it in the lifetime of the universe, right? So that is the kind of speed up that quantum computing, at least on paper, ultimately promises, for those specific problems, for which we have quantum algorithms, as I always stress. Okay, but what we're now trying to do is, with a noisy device of 50 or 60 qubits, just investigate whether that kind of scaling speed up is for real, right? And so we're not yet doing anything that no classical computer can do, right? We don't want to be, because if we were, then we wouldn't even be able to verify the results, right? The way that these experiments work. Okay, but we're showing that you can use one chip running for a few minutes, and it can take samples. Where if you wanted to take the same kind of samples that would spoof the same statistical test with a classical computer, then as far as we know today, you would be needing a gigantic cluster of maybe hundreds of thousands of cores running for days. Okay, and the reason for that gap really just is the size of the Hilbert space, right? So I think once you can do that, then again, the burden of proof really shifts to those who say that that this is not a quantum computational speedup.
So we got a question actually when you referred directly to the size of the Hilbert space. I will ask a question in the chat about whether there's a proof then that you can't beat quantum computation with analog classical computation.
Well, I would say that okay, so proof is a mathematical concept, right? And so I can't mathematically rule out that there is some analog computer that could even solve NP-complete problems in polynomial time, or do all kinds of crazy things. But I don't believe that. Okay, and the analog computing proposals that we've seen to try to go beyond Turing machines, have been incredibly unpromising, right? That's a really important point for people to understand, right? That they are often based on they're not actually scaling up to solve truly hard problems, and we know and I don't believe that they can. I think that when in analog computing, for well understood reasons, kind of noise is going to kill you. Or another way to say it is that the analog of the fault tolerance theorem, is just not true for classical analog computing, right? With classical analog computing, you really can have a tiny error, anywhere that will just get chaotically amplified over time, to the point where it kills the whole computation.
So let me ask you one last question, seeing as though we're almost out of time.
Sure.
You talked about the Wright brothers, and you had the impractical airplane that led to practical airplanes. So kind of 2 or 3 questions that we got combined here.
Okay.
What do you really think is going to happen then in the next decade or so? Where are the real opportunities for quantum computing to do something practical? And equally, to what extent are these experiments you talked about, the Google one and the USTC one, laying the foundations for that in the way that the Wright brothers did?
Yeah, well, I try to studiously avoid making predictions, right? Because if I had any skill at that, then I wouldn't be a professor. I would be an investor, and I would be rich, right? So, I think that it is obviously a very exciting time for quantum computing right now, because this was for most of the 20 plus years that I've been in this field. It was sort of an academic enterprise, and just within the last 5 years, it has become, for better and for worse, a commercial enterprise, partly, right? And you have, a bunch of startups. You have Google, IBM, Microsoft, Amazon, all investing in this. You have, governments, including the U.S., the EU, China, making major investments. And I am optimistic that within the next decade, we will start to see, quantum computers with, 50 to 100 qubits or 200 qubits that are really, programmable, and that we can maybe start to use to do some things that are interesting, maybe interesting for science, interesting for condensed matter physics, maybe even interesting for chemistry, right? And that would start, giving us an ability to simulate nature at a quantum scale and do something interesting. Now there are also constant claims about quantum computers being, usable in the next 10 years for solving optimization problems in machine learning. That, I think, is like 99% bunk. Okay, that is marketing hype. And because even if you had the perfect quantum computer, we just don't know how you would get a speed up for those problems. So I think that there's, there's a lot of smoke, there's a lot of hype, but I think that there's going to be some genuine progress as well, and I'm looking forward to it. All right, so I really apologize that I have to run, but thank you all for listening.
Thank you very much too, Scott, for the really interesting talk. It was great to have you here at the Quantum Science Seminar.
Okay, great. Okay, bye.
We'll pass back to Sebastian.
Okay, bye.
Yeah. Thank you also from my side, Scott. And let's wrap it up here and tell you that next week on May 27th, we will have yet another very interesting talk by Markus Aspelmeier, who will tell us about quantum optomechanics. You should also check out our sister seminar, the Virtual AMO Seminar, where tomorrow they will have our very own Christian Gross, who will speak about spin and density cross correlations in Hubbard systems. If you want to get notified about what we do, please go to our website, quantumscienceseminar.com. Subscribe to our email list, our Google Calendar, follow us on Twitter, please. And with that, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.